Hello everyone, welcome back to Zeta Factor. Today we will look into Fermat method of infinite descent. So what is Z? It's called FMID. It is very intuitive idea. Let's imagine that you have a solution to some Diophantine equation. It doesn't matter which one. But then Fermat method of infinite descent is a way to prove that there are no solutions by contradiction. Let's assume you can build a solution to this equation with x1 minimal solution. And because they are all positive integers, there should be some minimal x1. Let's assume that you can prove that by having solution to this Diophantine equation with x1 minimal, you can find some another solution x11 which also would be part of the solution but with x11 less than x1. In this case, you can build an infinitely descending sequence of integers, but naturally that can go forever because all of those are natural numbers, and by contradiction you will prove that original Diophantine equation does not have solutions. Let's illustrate this method on example of the following problem. This is problem from my favorite book. Find all triples x, y, and z of positive integer solutions to the equation x in the power of 3 plus 3, y in the power of 3 plus 9, z in power of 3 minus 3, x, y, z equals 0. How we are gonna approach this? So first of all, let's notice one thing. So we can see clearly that there is 3 here, 9 here, 3 here, and of course it's 0. 3 divides x. It is obvious that trivial solution 0, 0, 0 is a solution to this equation. It's not a solution in positive integers, but we will prove that there are no other solutions in non-negative integers. As we can see that 3 divides x. Let's assume that x1, y1 and z1 is a solution where x1 is minimal across all possible solutions to this equation, and x1, y1 and z1 positive integers. As we can see that x1 divisible by 3, so we can write like this. Let's plug that into the original equation. We will give, let's divide by 3 and rearrange. It's become obvious then if x1, y1 and z1 is a solution, then y1, c1 and x11 is also a solution to the same equation. But now we see that y1 divisible by 3. So we apply same methodology and then plugging it back, we will get that z1, x11, y11 is also a solution to original equation. Repeating the same argument, because 3 now divides by z1, we see z1 equals 3z11. Applying it again, we will prove that x11, y11, z11 is also a solution to original equation. But here's a contradiction. x11 less than x1. This is because x1 equals 3x11, which means we found a solution with smaller x. This is a contradiction to the fact that we picked x1 as a minimal solution. So if there is such solution where x1 is minimal, we always can find one which is less than z, which proves that there are no other solutions in positive integers to the equation. Thanks for tuning in to Zeta Factor today.